In this lecture, we are going to look at I/O control. We shall begin our discussion by looking at the concept of conditional and unconditional I/O. Unconditional I/O is when the peripheral device is always ready to receive or send data. As examples, 1. A 7-segment display is always ready to receive and display data sent to it and at any time. 2. When a simple switch is read, valid data is always obtained and at any time. Conditional I/O is when the device sends or receives data only when read. As an example, an ADC can only be read from after the AD conversion has been completed. Handshaking signals are control signals that are used to manage the exchange of data between a conditional I/O device and an I/O port or a microprocessor. Let's look at an ADC as an example of a conditional I/O device. An ADC has an analog input pin and a set of digital output pins. In addition, it typically has 3 control pins. The start pin is the pin on which a signal is asserted to start the conversion process. Analog to digital conversion takes a finite time. The busy pin is the pin on which the ADC asserts a signal to indicate that the analog to conversion is still in progress. The output enable pin is the pin on which a signal is asserted to make the ADC to place the outputs on the digital output pins. The digital output pins allow the transfer of data from the ADC to a microprocessor or any other reading device. The control pins allow handshaking signals to be exchanged between the microprocessor and the ADC. Programmed I/O is when the microprocessor runs a program to control the exchange of data between it and the I/O device. For conditional I/O, the program may require a loop. As examples, when controlling an ADC, there may be need to continuously poll the busy line while waiting for an analog to digital conversion to go to completion. When using a microprocessor to control a keyboard, there may be need to continuously poll and wait for a key to be pressed on the keyboard. Let's illustrate programmed I/O using the ADC example. The microprocessor communicates with the ADC through an I/O port chip. Port 1 is connected to the ADC digital output pins, and port pins 2.0, 2.4, and 2.1 are connected to the ADC control pins as shown. To start the ADC conversion process, the microprocessor asserts the start signal through port pin 2.0. During the conversion process, the bus signal will be asserted. The microprocessor, therefore, will poll port pin 2.4 until the bus signal is deasserted. When the bus signal has been read as deasserted, the microprocessor sends the output enable signal through port pin 2.1. The ADC responds by placing the output on the digital output pins. The microprocessor then reads port 1 so as to read in the output of the ADC. As an exercise, do this question from chapter 6 tutorial questions. The question requires you to develop a subroutine that can be used to control an ADC using the 8086 microprocessor. Strobed I/O is when the port has inbuilt circuitry to exchange handshaking signals with an I/O device. This means that the handshaking signals are generated in hardware. Therefore, there is no need for a microprocessor program to be developed to handle the handshaking signals. The output buffer full signal is a signal from the port to an output device to indicate that the port has something to send to the output device. When the output device is ready, it reads in the data from the port. To indicate that it has read in the data, the output device uses the acknowledge signal. Thus, the acknowledge signal is a signal from the output device to the port to indicate that the output device has read in the data from the port. Strobe is a signal from an input device to the port to indicate that the input device has new data for reading in by the port. When the port is empty, it reads in the new data from the input device. If the port is not empty, it indicates this state using the input buffer full signal. Thus, the input buffer full signal is a signal from the port to an input device to indicate that the port has data that has not yet been read by a microprocessor. In other words, the port cannot accept any new data from the input device. The input device, therefore, will need to wait until the port is ready to read in the new data. Interrupt is a signal from the port to the microprocessor. It indicates one of two conditions. If the port is an output port, interrupt indicates that the port is empty and can receive new data for output from the microprocessor. If the port is an input port, interrupt indicates that the port has data read in from an input device for the microprocessor to read. In this illustration, we want to show the sequence of events that occur when reading a data item from an input device such as a keyboard. The microprocessor controls the input device through a programmable interface device. The connection between the microprocessor and the programmable interface device is made up of the data bus, the address bus, the read control line, and the interrupt line. The connection between the programmable interface device and the input device is made up of a set of parallel data lines, the strobe handshaking line, and the input buffer full handshaking line. First, the keyboard sends the strobe signal to the port to indicate that it has data ready for reading by the port. If the port is empty, it responds by reading the data from the input device. Once the port has read in the data, it indicates that it is now full and therefore cannot accept new data through the input buffer full handshaking signal. The port then sends an interrupt to the microprocessor unit to indicate that it has data that it has read from the input device. The microprocessor responds by reading the data from the port. The port, once the data has been read from it, indicates to the input device through the input buffer full signal that it can now accept new data. Let's apply probed I/O to the ADC example. Port 1 on the I/O port chip is connected to the digital output pins on the ADC. Port pin 2.0 is connected to the start pin on the ADC. This means that the microprocessor will write to port pin 2.0 to start an analog to digital conversion. The probe pin on the I/O port chip is connected to the busy pin on the ADC. This means that as soon as the busy signal is deactivated, that is, as soon as an analog to digital conversion is completed, the port chip is going to be probed. The input buffer full pin on the I/O port chip is connected to the output enable pin on the ADC. This means that as long as the port is empty, the ADC is going to be enabled to place the output of a conversion on the digital output pins. As exercise, do this question from chapter 6 tutorial questions. The question requires you to develop a main program and an interrupt service routine to enable the Intel 8086 to run an ADC using interrupts. There are 4 operation modes of ports. These are basic input-output mode. In this mode, a port operates as either a parallel input port or a parallel output port. When a port operates as a parallel port, data is exchanged in parallel form between the port and an I/O device. This means that the data is transferred as bytes or as such other units that are made up of a number of bits. There are no handshaking signals in basic input-output mode. Bit input-output mode. In this mode, each pin within a port can be individually manipulated to write or read a single bit of data. Strobed I/O mode. In this mode, a port operates as either a parallel input port or a parallel output port. Handshaking signals are used to control the exchange of data between the port and an I/O device. Bidirectional mode. In this mode, a port can accept data in either direction. That is, it can operate as either an input port or an output port. Handshaking signals are used. Generally, port chips are configurable to make the ports on them operate in any one of the modes that we have just described. This exercise is meant for you to acquire more knowledge on the operation of port chips. You may optionally do these questions. The questions will request you to research on Zilog and Intel port chips. After that, you will be required to develop code snippets that can be used to work with the port chips. There are some peripherals that have built-in port capabilities. These peripherals can be directly connected to the system bus without the need of a port in between them and the microprocessor. The circuitry of such a peripheral consists of a circuitry to carry out the function of the peripheral, a port register to enable direct connection to the data bus, as well as control and status registers as necessary to control the operation of the peripheral. Examples of such peripherals are timers, counters, the serial interface port, and the disk controller. This illustration shows a disk controller. The controller has a buffer memory to hold the data that is to be written to the disk or the data that has been read from the disk. The data register is used to interface the controller to the data bus. The control register is used to control the operation of the controller and hence the disk. The status register is used to hold the status of the controller and hence the status of the disk. Direct memory access, DMA in short, is a technique of transferring data directly between an external I/O device and the main memory of a microprocessor-based system. During DMA, a controller known as the DMA controller controls the data transfer. In other words, the DMA controller controls the system bus and the microprocessor does not have control of the system bus. The diagram shows a typical DMA controller and the associated control signals. The DMA request lines are the lines that are used by I/O devices to request for DMA through the DMA controller. The hold request line is the line that in turn is used by the DMA controller to request for control of the system bus from the microprocessor. The hold acknowledge line is the line that is used by the microprocessor to acknowledge and therefore grant control of the system bus to the DMA controller. The DMA acknowledge lines are the lines that are used by the DMA controller to acknowledge the respective DMA requests. They are used to indicate to the I/O device that the request for DMA has been granted. Address lines, data lines, and control lines are the lines that are used by the DMA controller to control the system bus during DMA. This diagram shows the hold and the hold acknowledge pins on the Intel 8086 microprocessor. These pins are available in the minimum mode of the processor. Let's illustrate the sequence of events that occur during DMA. Initially, the peripheral device sends the DMA request to the DMA controller. The DMA controller in turn sends the DMA request to the CPU. The CPU responds by putting its system bus in a high impedance state, after which it acknowledges the DMA request to the DMA controller. The DMA controller then sends a DMA acknowledge signal to the peripheral device. After that, data can be transferred directly between the peripheral device and the memory. During DMA, the DMA controller controls the system bus by generating the necessary addresses and control signals. Serial communication is the transfer of digital data between two devices in which the data bits are transmitted one after the other. The transmitter receives parallel data and converts it into serial data that it then transmits to the receiver. The receiver receives the serial data and converts it back into parallel form. Generally, the least significant bit is the first bit to be transmitted between the transmitter and the receiver. The number of bits that are transmitted in a second is referred to as the baud rate. There are two types of serial communication, and these are synchronous communication and asynchronous communication. In synchronous communication, the communicating devices share a clock signal to synchronize the communication. Each data bit is transmitted in one clock cycle. In asynchronous communication, the communicating devices have separate clocks, and these clocks are preset to a common speed to synchronize the communication. A universal synchronous asynchronous receiver transmitter is required in serial communication. It serves two purposes in the communication system. The first one is to convert parallel data into serial data for transmission, and the second one is to convert the received data from serial into parallel form. A USART is connected between the microprocessor and the source or destination of the data. The diagram shows the use and connection of USARTs in a communication system. USART 1 receives parallel data and converts it into serial form. It then sends it out through the TX pin. USART 2 receives the data from USART 1 via the RX pin. It converts it into parallel form and sends it to the destination of the data. Level translators and modems may be required in a communication system. A level translator is used to convert TTL voltage levels into voltage levels that are suitable for the communication channel. As an example, the MAX 232 is used to convert TTL voltage levels into plus or minus 15 volts that is suitable for RS-232 communication. A level translator is inserted between the USART and the communication channel. There are situations when the data is transmitted in modulated form. In such a situation, a modem is required to modulate the data for transmission as well as demodulate the received data. A modem is inserted between the USART and the communication channel. A communication protocol is the electronic language which is used when two devices are communicating. It defines the quantity and uses of signal lines, the voltage levels that are used, as well as uses of bits and bit slots, among others. Examples of serial communication protocols are SPI, USART, and I2C. For your own benefit and in your own interest, you may do this question from Chapter 6 Review Questions. It is a question that requires you to research on a couple of communication protocols.